Good morning, everyone. I'm really happy to be here and nice to see the interest. Can you hear me in the back? Great. Um, so I'm going to talk about. I'm a mechanical engineer, and I've been working in the assistive devices space for nearly 30 years now. My interest in assistive technology started when I was a BTech student. Um, when I was a BTech student here, and I did my final year project, and it's kind of become my life's work in some sense. I was hooked because I felt this is an area where I can see tangible benefits to the work that I do, and that was important to me. Um, so I'm going to talk a little bit about engineering for empowerment because we are at the Empower conference. It seemed like that would be a good title for my talk. Um, so the motivation for the work that we do is because there are over 30 million people in India alone who are affected by locomotor disability. And there are various causes for locomotor disability. And for some of us, it will be progressive as we age. Um, so aging is also one of the causes, and some of us may need assistive devices as we get older. But there are other causes of disability, which could be temporary or permanent. And for any kind of movement disability, it requires both rehabilitation as well as assistive devices. Because even with assistive devices, in many cases, you need training on how to use them. You need to have a certain level of fitness to be able to use them. So rehabilitation is also an important aspect of that. And at R2D2, we use our knowledge of biomechanics, mechanical engineering, mechanism design to create these kinds of devices. And the other thing is, we also work on other aspects to help translate these devices to the market, because I could have a lot of nice prototypes in the lab, but unless I translate them to the market, I'm not going to have the impact that I want to have. So if you look at the types of solutions for assistive devices, one extreme, you have very simple solutions, very low cost. Other extreme, very high-tech solutions, and both have their advantages and disadvantages. Sometimes the simple solutions are too simple to even be functional, leading to rejection of the device. And in the case of the high-tech solutions, sometimes they're very expensive, and so is it too high-tech? In many cases, if you're not able to translate something from the lab, you may be working on the latest and greatest technology, but if it doesn't translate out of the lab, it's not going to have the impact. And if you're working in assistive technology, without impact, it's no good. Without impact, it's just no good. So we try to bridge the gap. We are trying to work on functionally appropriate devices. We want them to be high quality because it's largely driven by a donation market, but we don't want people to get devices that they cannot use. And yet we want them to be affordable for the same reason, so that everybody has access to uh, appropriate assistive devices. I'm going to just speak about the role of engineering in ensuring that we bridge this gap. There are lots of aspects to it, but because there's a crowd of assistive technology entrepreneurs and young students, I just thought I'll share the development frame. It all starts with the need. So unlike other technologies where you have an idea, you develop something, and then you try to figure out who it is for, in assistive technology, if you're working in this space, you figure out what the need is. You figure out who you're designing it for and talk to them and find out what their needs are. And that's going to form the basis for your design requirements. And then, and only then you start looking at your objectives of your design. And then, of course, you have the standard, process that you follow. You do a literature review, you look at all the other products in the landscape, Then you come up with conceptual designs, synthesis, analysis. You have to do all this. There has to be a process. Otherwise, it's just jugaad. Jugaad may work for one or two things, but if you want something to be high quality, it has to be properly engineered. And of course, you do prototyping, mechanical testing, etc. And this is an iterative process. And then, of course, you will have outcomes, in terms of papers, patents, and then pre-commercial prototype, and hopefully get to commercialization with the industry. So the need, if there's one thing that you get out of this talk, the need is what you need to work on. If you're a startup in assistive technology, do not, think that you will figure out who it is for later. So an example, why a standing wheelchair? Right? So there was enough literature, there's enough in the literature, enough studies that show that there are benefits to standing. I think all of us are also encouraged to get up and walk around every once in a while, stand, get your circulation going. We all know that. But for people in a wheelchair, it's not a choice. Even if they wanted to stand, they may not be able to stand. And so that could lead to secondary health problems. And therefore, standing as therapy is very important for them, but they may not be able to do it independently. And so the functionality we were looking for is, integrating the standing functionality into a wheelchair, because you want to go to the gym to exercise, it's very likely that you won't do it that often. Okay? If you make exercise, so if you climb stairs when you have to go to work, or you walk from one place to another, then it's more likely that you're going to get that kind of exercise. So integrating it into something that you're using all the time is a better way of ensuring that it's used for its purpose. And besides the health benefits, which research has proven, and which we didn't have to go and try to justify, there's also research that shows what an effect it has on the self-esteem of a user, on the self-confidence, to be able to stand in a room full of people who are standing. It does a lot of, there's a lot of psychological well-being associated with it. So the need was pretty clear. And then we just we looked at some existing wheelchairs and we thought, this is just a mechanical engineering device. We can do this. So we started looking at, so this is one of the early trials at CMC Vellore. You can see our objectives were clear. It should be operable just just mechanically with your upper limb strength. And you can see here that this user is not applying a lot of effort. You're essentially lifting your body weight to the standing position, and but with just a little bit of upper limb effort. So there's a lot of engineering that goes on in the design of the mechanism, in ensuring that the effort that's applied by the user is minimal, in customizing it to various users, because various body weights, they can apply different amounts of effort. So the principles of spring balancing that we use here, they have to, spring balancing, a very simple example, in your cars, right, the boot. You're able to lift that very easily, even though it weighs a lot. Okay, it's a big weight of steel, but because there are gas springs in there that help you, that balance that weight. That's why the effort that you require to open your hatchback is so low. Same principle here. The effort that's required is kind of multiplied to actually do the lifting of the body weight by the linkage as well as. So there's a lot of engineering that has to go, analysis that has to go in to designing these devices. And this gives you a very quick snapshot of the number of versions we had to go through, because like I said, it's an iterative process. So in various versions, we were handling different things. We first, proved the standing, that standing can happen, etc. So I won't go into the details of it, but it's important that even if the first version is tested by non-disabled people, you have to get the actual users to test your device pretty early on. You have to involve them because there are issues that will come up that you would not have predicted. Similarly, for the prosthetic knee, our knee joint, we walk without really thinking about it. But the knee, there's a lot of biomechanics that goes into the way we walk. And the knee performs two functions. When I'm what it's called the stance phase, when I'm weight bearing, it doesn't give way, it doesn't buckle and let me down. At the same time, it has to bend to move forward, to allow me to progress forward. And designing a knee, therefore, is very challenging because you have two competing requirements. And so the simplest solution that people walking on uneven terrain come up with is to just lock it. You just lock it so you don't buckle when you're trying to walk. What does that cause? Your gait is awkward. You consume more energy. If you try walking with a locked knee, you'll know what I'm talking about. You may have seen people walking from their hip, trying to clear the ground because they can't bend their knee. And therefore, again, we thought, okay, why has this problem has been solved in other places? Let's first look at existing solutions, compare them, identify parameters, biomechanical parameters that are important for walking on uneven terrain, and figure out whether any of the existing knees meet that requirement. And surprisingly, we found that nobody had done this kind of analysis before, and we found that the existing knees were not really suitable for Indian conditions. And that is how we did optimization and came up with the geometry of Kadam, and I'll play a quick video.
Progress. The ability to move freely not only helps in performing day-to-day functions, but has a bearing on one's physical and mental health. For persons with locomotor disability, mobility is often far-fetched, depriving social inclusion and participation. The WHO states that only 1 in 10 people in need have access to assistive technology, and they are not available in adequate numbers and affordable prices. The TTK Center for Rehabilitation Research and Device Development, R2D2, at IIT Madras, headed by Professor Sujata Srinivasan, has been working to fill that gap. Following the Arise, NeoFly, and NeoBold, the most recent innovation from R2D2 is an indigenous polycentric prosthetic knee joint suitable for persons with transfemoral or above knee amputation. The 4-bar knee called Kadam. Kadam has advantages over a hinge joint because of the multiple axes of rotation, which provide the user greater control over the prosthesis while walking and a maximum knee flexion of 160 degrees, which makes it easy to sit in cramped spaces like buses and autos. It is designed for durability with high-strength stainless steel and aluminum alloy, along with hard chrome-plated EN8 pins and high fatigue life polymer bushings. Kadam is India's first indigenously developed polycentric knee for an above-knee prosthesis, AKP, under the Make in India campaign in association with Society for Biomedical Technology, SBMT. The knee is affordable and at the same time of high quality and performance, complying with ISO 10328 standards, including 30 lakh cycles of fatigue testing. It provides stability, reduces the risk of stumbling, and its patented geometry is specifically optimized for use on uneven terrains. Through Mobility India, extensive clinical trials have been conducted, the results of which have ensured the design is user-centric. Users instantly recognize the stable nature of the knee. The ability of the user to let go of the safety of parallel bars in the very first trial is a testimony to the performance of the knee. For thousands of above-knee amputees in India, Kadam makes it possible to walk with a more comfortable gait. Not just mobility, Kadam aims to improve the overall quality of life of users, make them an integral part of the society, and instill confidence in such individuals to face the daily challenges in life.
So rehabilitation is also very important to bridge the gap between, after the disability, after the hospitalization, when they come home, they have to be rehabilitated in order to be able to use an assistive device effectively. And again, there's a scarcity of trained healthcare professionals to do the rehabilitation, so technology can help fill that gap. In association with CMC Vellore, we've developed a robot for hand neurorehabilitation, which is called Pluto, plug and train robot. You can also see that in the exhibit. And what's simple is that I call it the mixing model, right? You have one motor and you have different blades in a mixie. Here, you have different attachments to train different degrees of freedom of the hand. And so there's all the passive mechanisms can be carried around in a hard case. You have a stand that can easily, you can start rehabilitation right after the injury, like after a stroke at the bedside. Because usually these robots are very complex. You have to take them to where the robot is instead of bringing the device to the bedside of the person doing it. So you can train various hand motions. This is again a startup that we are working on to do this. And it's gamified so that the person persists with the therapy, so that it's fun for them to do. Otherwise they'd just be making a movement, several hundred times, and it's not going to be a pleasant experience. So we have trials running in over 7 rehab centers across India, and we're also creating a home-based version so that they could take it home and continue with the therapy, a simplified version. And it also gives feedback, it collects data about the therapy so that the therapist can, have quantitative feedback on how the therapy is going. So these are some of the things that we are working on. So engineering with a multidisciplinary approach is needed to meet the challenges of assistive devices. Appropriateness, acceptance, affordability, access, and awareness. Just an overview of the activities. We've realized technology alone is not enough, so we do awareness programs. We're probably the only center with a clinical team working in this area. We have occupational therapists, physical therapists as part of we have peer trainers, expert wheelchair users, who are now training other people on wheelchair skills. And we're also now going to open an experience zone here in the research park in collaboration with them. ICMR has given us funding to open a national center for assistive health technologies. This will be one of 4 centers across India. IIT Delhi is one of the other centers. So just wanted to give you an overview of what we do and how engineering is important for creating empowering devices. Thank you so much. The center is on LinkedIn as well as YouTube. I don't have any personal social media accounts, but we have a web page link for the center. So if you just Google R2D2 IIT Madras, you can see all the videos. You can see whatever you need. So, happy to take if you have. You can catch me. Oh, please. Right. I didn't mention that in the last slide, but those are the 4 products that have been the Arise standing wheelchair has been commercialized through an industry partner. NeoMotion is a startup from R2D2, which has commercialized NeoFly and NeoBolt. So altogether in the last couple of years, I think there are probably a total of 3,000 plus devices out in the market of these. You can see NeoMotion is here at the exhibits. The polycentric knee, we have transferred the technology to Mobility India, which is an NGO and also runs a bachelor's in prosthetics and orthotics program and a master's program as well. So we are trying to train the next generation of P&O professionals in using devices like the knee. So that has not hit the market yet, but it's in the process of doing it. So 4 so far. We are looking at the hand neuro rehab device because it's now undergone quite a few trials. We have a couple of other startups in the works also. So, no, not yet. So it has been basically so we support the R&D right up to the point of commercialization at R2D2 by I didn't talk about the grid model, but grants, research, industry dissemination, the four pillars, and because we can get grants at IIT we do the commercialization up to the point of commercialization. But now, NeoMotion is now on the road for the last 2 years, and knock on wood, so far so good.